right, everyone. How are we doing today? Okay. How was break? All right. Okay. All right. I'm glad to hear that people are doing all right. Break was okay. Um, just so everyone knows where we are with how things are going. We're going to have our Chapter 3 exam a week from today. So it'll be the 21st. Is that right? Okay. So the idea is that we'll have, basically due to a quirk in the schedule that was caused by us being on break earlier this week, have an extra review day for this chapter, which is fine. And so let's jump into talking about everything that was going on in our previous lessons. Okay, so chapter 3 focuses on second order linear equations with constant coefficients. What that means for us is that we write the differential equation to have the form looks like this. Ay double prime plus by plus cy equals g of t. And everything in the section that we worked with started with kind of one base assumption and then built from there. We started with the idea that we could guess that the solution had the form y equals e to the rt, and we applied this primarily to solve the homogeneous problem, which is the differential equation when y is equal to 0. Or sorry, when g of t is equal to 0, excuse me. So if we have a 0 right-hand side, we assume that our solution has this form. And if we make that assumption, what we can do is plug this expression in. And after differentiating and factoring, we see that we get this expression, and we refer to this part here as the characteristic equation. Clean that up a little bit. Okay. The idea is that through some means, and we can always, at minimum, use the quadratic formula if necessary. Determine the roots of the characteristic equation, and these represent the value of r that give us the solutions to the homogeneous case. There are three cases that arise. the case where we have real distinct roots. So R1 is not equal to R2. And both of these are real numbers. This tells us that the solution y of t will be constructed of a linear combination of these two solutions. Okay, and it's going to look exactly like this. The second case is when we have real repeated roots. So R1 is equal to R2, and we'll just call this R for simplicity, and R is a real number. Okay. This tells us that the solutions are going to be a linear combination of these two functions, e to the RT and t e to the RT. We showed the origin of this t by using the method of reduction of order when we covered this section. Okay, so the way that this works out basically is that we broke the differential equation down into two sub-differential equations that look like this, right? We solve the equation, and then after solving the equation, we solved this equation here, which is a linear first order equation. And then after we solved the linear first order equation, we went through and solved the equation where we replaced this with v and then turned the right hand side into what the solution to the other equation was, right? So in this case, it was e to the RT. And then that gave us the solution to the second linearly independent solution to the differential equation. This is covered in detail in the online notes. I just kind of wanted to remind everyone that we've discussed previously where that is, and the details are available. It is not some unknown bit of sorcery. Okay. The third bit is if we have complex conjugate roots. That is that R is equal to lambda plus mu times I, where lambda and mu are both real numbers, representing the real and imaginary part of the complex number, respectively. Okay. The solution in this case is something that arises from this formula here, commonly referred to as Euler's formula, where theta ends up being mu here. And the basic idea is that we have e to the lambda plus mu I times t, right? We can write this like this. Because if I have a sum in the exponent, that means that I can write it as a product. Okay. And then this part gets turned into sines and cosines according to the formula, where mu t is what we take to be for theta. Okay. That is where the expression e to the lambda t cosine mu t plus, sorry, c1 cosine mu t plus c2 sine mu t arises from. Okay. And as a reminder, again, the actual expression that we get from doing this looks like e to the lambda t cosine mu t plus I sine mu t and e to the lambda t cosine mu t minus I sine mu t. Those would be the two expressions we get, right? Ultimately, what we want is to have just two linearly independent solutions, right? We can use the Wronskian to show that this and this, okay, just e to the lambda t cosine and e to the lambda t sine are linearly independent. That's enough. That means that it forms a fundamental family of solutions, and we can use a linear combination of e to the lambda t cosine and e to the lambda t sine to express our solutions. That's why we're able to reduce it to this form. And in addition, any potential complex numbers get absorbed into that coefficient, which is why I don't write I either. I don't need it. Okay? And it turns out to be a consequence of the fact that when we set up our problem, if these are real numbers, it will never be the case that C1 and C2 end up being complex valued. So if A, B, and C are real, C1 and C2 will always be real. Okay, that's why the complex numbers kind of fall out of the problem. If I allowed my coefficients to be complex valued, which is something that you might see if you were saying doing problems involving current under certain circumstances, then you may get imaginary values that show up in your solution. Okay, and for those of you who may do some work in EE, that will be something that you see. Okay, so this is all information that you need to have memorized. Okay, you should be able to, in a very small amount of time, come up with the roots of the characteristic equation and just write down one of these answers. Okay, so when it comes to writing the exam, I'm going to assume that you know how to do this and can do it quickly. So it's not going to feature heavily into the time budget for the exam. Okay. You should be happy if all I ask you to do is find the general solution to a homogeneous equation. Okay. The problem takes less than 2 minutes. Now, because of that, of course, we need to make sure that we're careful as we transition into the more sophisticated problems, which are the non-homogeneous cases. Okay. Now, if we have problem that looks like this, where we have differential equation, and it is the case that g of t is not equal to 0. Okay, not identically equal to 0, rather. I drew a triple equal sign. Okay. Putting a no sign through that means that the function is allowed to assume the value 0, but it is not always 0. Okay. So, under this circumstance, there are two cases of problems that can come up, or two solution methods that we can attempt, however you want to think about it. Undetermined coefficients, and then also, we'll write it down here, but I may need to move it down if I need more space, variation of parameters. Okay. For the method of undetermined coefficients, we look at right-hand sides that are in some sense nice. And I'm making finger quotes with my hands for those of you who can't presently see me. That means that, sorry, we would have a right-hand side that looks something like this. 3 times cosine 2t, or e to the minus t sine 5t, or a polynomial on the right-hand side, or what other kinds of things? I don't want to forget something. Oh, that's right. A polynomial times a trig function or something like that. Okay. Or a linear combination of these sorts of things. Okay. Now, for the method of undetermined coefficients, the key to the whole thing is what kinds of guesses do we make in order to give us an expression in which we are trying to determine the undetermined coefficients. So if we have G1 here, the particular solution that we would guess to go along with this would have to be some linear combination that can handle the fact that we have cosine of 2t. Okay, and we've discussed when we covered this during the regular lectures, the necessity of having sine, because if we take the derivative of cosine, a sine term will show up. And that'll get involved in the things that we end up adding up and needing to be equal to the right-hand side when we plug our particular solution into the differential equation. Okay. For the particular solution associated with G2, we have a similar situation where we're going to need both cosine and sine in order to handle this expression. Yeah, and the question here is, it doesn't if it matters whether or not it's cosine and then sine or sine and then cosine. It doesn't matter. No, it's just as long as you have to be consistent in the way that you write it, but it doesn't matter the way that you label them. Okay. For the particular solution associated with G3, you will need a polynomial that is high order enough to be able to encapsulate all of the information for the polynomial. Since this is a quadratic, your guess has to be a quadratic. And it has to have all of the terms. Because if I differentiate t squared, I'm going to get a t. So I'm going to have a term that can handle that. Okay. For y4, this is the sort of thing we have to be careful about. Okay. Are we sure that this is a thing that we can handle using the method of undetermined coefficients? Because we know that if it gets too bad, then that will be a problem where it's necessary for us to transition to using a more sophisticated technique. Right? Okay. Now, you may not have a copy of the textbook at hand, but one of the things that I do want to point out is that at this stage, this particular problem is one that does show up, or at least something similar to this does show up in your textbook, but they're not ones that they ask you to solve by hand. They say make a guess as to what the solution might look like and then go from there, which I think is pretty funny. Okay, but because for this thing, the way that would have to work is we have a quadratic. But we also have sine and cosine. So maybe that's bad. Okay. And then just to let you all know, so that it's clear what the situation is here. Uh, these two things would be multiplied together. The other way that you could write this, of course, is just have these, and yes, these coefficients will have to be different. In your textbook, sorry, I might be looking at the wrong version of the textbook. In section 3.5, where we cover the method of undetermined coefficients, there's actually a table where they show this result, by the way, where you have to multiply by the appropriate order polynomial times sine of t, or sine and cosine. And then it also actually works if there was an e to the t factor too. Like, if there was an e to the t here, you just hit this with e to the t. Okay. So one of the things that I reserve the right to do on the exam is ask you to tell me what the guess would be, even for this really complicated part, right? I would give you this right-hand side and say, tell me what you would guess if you were trying to set up the method of undetermined coefficients. What should the particular solution look like? Okay, what form should it have? I'm not going to ask you to find, if it's a really nasty one, the actual coefficients, but I will ask you what the starting point would be. Okay? And that may include also giving you something like this, where I have three of these things and I add them all together and say, what does the guess look like? And the guess looks like those three guesses added together, all with different letters, right? So you might get up to GHI or something in the alphabet in order to write down all the coefficients, but it's just a matter of note keeping, right? Okay. So does that make sense? All right. And then the other thing to keep in mind, of course, is that if you do get into a situation where you're asked to solve a problem where you have three different functions that are added together or something like that, the way that this works, because we are talking about linear differential equations, is that each of those problems can be solved separately. I can find the particular solution for G1, then I can find the particular solution for G2, and then for G3, and then my answer for the particular solution for the entire differential equation is just the sum of those three answers. So you can synthesize the previous results to answer what is the particular solution for this. Okay. If our equation was nonlinear, that wouldn't work. Okay, so this is an extremely important consequence of linearity, and part of the reason why we stick to that for most of this class once we get to second order equations. Okay. The next method that we have is for variation, or sorry, there's one last note that I need to make about method of undetermined coefficients before we move on. Okay. My vocabulary. One of the things that you do need to be mindful for when you're using the method of undetermined coefficients is you have to ensure that for the method of undetermined coefficients, that the right-hand side, the function g of t, is not linearly dependent upon the homogeneous solution, or the complementary solution, whatever you want to call it. Okay? So if it so happens that we have a problem where say we have y double prime plus y equals 2 times sine. The characteristic equation for this is plus or minus I, or the roots of the characteristic equation are plus or minus I, which tells us that the complementary solution is going to be equal to a linear combination of cosine and sine. Right? This means that whatever guess we make for the particular solution is going to have to be modified somehow. Right? I'm going to have to multiply it by t in order to get it to work. Does that make sense? The more common version of this problem that comes up instead of this form would be something that looks like this, where you have y double prime plus 2y prime plus y, and then this would be like that. So this is r squared plus 2r plus 1. We can factor this. You get r equals negative 1. Okay. And so therefore, y of t is going to equal, or sorry, the complementary solution would be equal to e to the minus t plus c2 e to, or c2t e to the minus t, as we discussed previously, right? Real repeated roots. But if I look at the right-hand side here, I notice that it's linearly dependent upon my homogeneous solution. This is a problem. Because if I make a guess that looks like this, and plug this into the original differential equation, I'm going to get 0. Because plugging this type of function into the differential equation gives me 0. So some subset of it is also going to give me 0. That's why we have to modify the guess so that we avoid this problem. Okay? The most common technique that works is just multiplying by t, the number of times we need to multiply by t to not have this linear dependence anymore. In this case, one multiplication by t isn't going to do it because I already have t e to the negative t here. So I have to multiply by t squared in order to get it to not be linearly dependent. Okay? And this type of guess, again, arises from the method of reduction of order. The same place that we got our understanding of where this t comes from. Okay, we just didn't as explicitly go through that other case as we did the first one. Now, someone in the chat asked about the modified version, or why it was the case that needs to happen. Does this make sense now? It all boils down to linear dependence upon the homogeneous solution, which is why before we apply any of these methods, be it method of undetermined coefficients or variation of parameters, we need to make sure that we solve the homogeneous problem prior to stepping into these. Any questions here? Okay. All right. Now, for variation of parameters, we start off in the same place. We have some non-zero right-hand side. Okay. And in some sense, g of t on the right-hand side of our differential equation is not nice. Okay. Typically what that means is that it doesn't lend itself to be expressed in terms of linear combinations. It is not a polynomial. It is not sine and cosine. It is not e to the something times sine and cosine, or a polynomial times sine or cosine or e to the t or whatever. Okay, basically, if it doesn't look like a product of polynomials, exponentials, and trigonometric functions, or sine and cosine specifically, then it doesn't set itself up right with respect to linearity in order for us to be able to use the method of undetermined coefficients. So instead of that, we apply the method of variation of parameters. And the method of variation parameters is based on this idea. Where we solve the homogeneous equation, and after solving the homogeneous equation, we come up with the functions y1 and y2 that are part of our fundamental family of solutions for this expression. And those are what get plugged into this other form here. And we have unknown functions u and v, or u1 and u2 if you want to write it that way instead, doesn't matter. And we replace c1 and c2 with these function coefficients. And our goal is to figure out what properties must these function coefficients have in order for us to be able to solve the differential equation. Okay. If we plug this expression into the differential equation and do some algebra and calculus and work everything out, okay, we will come up with essentially a system of two equations and two unknowns. Okay, it will require that we add an assumption to this system of two equations and two unknowns in order to get everything to work out the way that we want it to, but the end result is a matrix equation in the following form. Okay, so this is our system of two equations and two unknowns. And your book does not write the problem, or does not write this method this way. Okay, it presents the formula for a variation of parameters in my opinion, in kind of a confusing way, not taking advantage of the Kramer's rule way that we've set things up here. Okay. But the idea for this expression is that you can now come up with formulas for u1 and for u prime and v prime, or u1 prime and u2 prime, however you decide to write it. By computing the following quantity. Again, this is an application of Kramer's rule. And I will write this way to remind you all that that bottom determinant in the denominator is actually just the Wronskian of y1 and y2. Okay. What this does is it gives us expressions for u prime and v prime, and then once we have those expressions for u prime and v prime, we integrate those expressions to get u and v, and then once we have u and v, we can plug them back into this expression in order to determine the particular solution to the differential equation. Okay, so the rest of the methodology here is integrate u prime and v prime. Okay, all right. I heard noises and I thought it was raining again somehow. Just someone going through their backpack. Okay, so plug those functions back in and simplify. Everything's fine. So does this all make sense? Okay. Now, I know that we've covered several things throughout the chapter. Okay. And what I wanted to do here was go through and kind of in one cohesive whole explain everything, put it into context, and then make the process clear. Okay. On, of course, in an in-person exam, the point is that you are familiar enough with the process that you can come in and demonstrate to me how to do it, right? Okay. What we don't want to be is in a situation where we're trying to remember what the steps are for variation of parameters and get stuck and not get the opportunity to solve whatever problem it is because we're just kind of lost in the muck. Okay. All right. Now, I'm just going to pick a problem and start going and see what happens. All right. So let's see what's going to happen here. All right. Now, just for clarity, I'm just picking a problem out of the exercise list in the textbook, and then we're going to see how it goes. Okay. So we have here a problem that looks like it's most likely going to be suited for variation of parameters, right? Okay, that right-hand side is not what we would classify as nice. But we also want to make sure that before we get into the variation of parameters stuff, because we need to do it, that we take a look at the characteristic equation for the homogeneous case and solve that problem. Okay. So we see that we get r equals 1 here. We have a situation where we have real repeated roots, and that tells us that the complementary solution is going to be c1 e to the t plus c2t e to the t. And what we want to do now is set up variation of parameters for this problem here. Okay. Our matrix equation that we want to construct for this has in the top row e to the t and t e to the t. And then in the bottom row, the derivatives of both of those functions. So e to the t and e to the t plus t e to the t. We multiply this times the vector u prime v prime. And the right-hand side is 0 and g of t, which for this problem is e to the t over 1 plus t squared. Okay. So now we want to, as above, set up our equations for u prime and v prime. We're going to have 0 and e to the t over 1 plus t squared. And here t e to the t and e to the t plus t e to the t. And then let's go ahead and, for the sake of saving ourselves a little bit of trouble, compute this Wronskian on the side. Which looks like this, right? Okay, so that means our denominator is just e to the 2t. And then we can put the rest of this together. In the numerator, we are going to have t e to the 2t over 1 plus t squared all over e to the 2t, which simplifies to just t over 1 plus t squared. And then for v prime, yes, you're correct. Sorry, I lost the minus sign here. Sorry about that. Okay. For v prime, we have e to the t and e to the t here, and then 0 e to the t over 1 plus t squared, and in the denominator, e to the 2t yet again. For the numerator, we're going to have e to the 2t over 1 plus t squared minus 0, and then e to the 2t in the denominator of the compound fraction. This simplifies to this. Okay. Fortunately for us, this means that both of these expressions are easy to do the integrals for. That right-hand side was probably a little bit worrisome to start with, but we end up with something that isn't all that bad. For this integral, the way that we compute it is we set, we'll say p equal to 1 plus t squared. That means that dp is going to be equal to 2d dt. We have an extra factor of 2. That's where the 1/2 comes from. And then after our substitution, we end up with the integral of negative 1/2 1 over pdp. And the integral of that is, of course, just the natural log of the absolute value of p, which we replace to get 1 plus t squared. Okay. And then for v, the integral is arctangent. Okay. And so we can now put into our expression these functions that we have determined. We get negative 1/2, the natural log of the absolute value. We can drop the absolute value because 1 plus t squared is a quantity that is always positive. And then e to the t was y1. T to the, wait, what's it? Yeah. T to the t was y2. And so there's our expression here. It is convention to go ahead and factor out the complementary solution and put it up front. And whenever I'm doing this kind of multiplication with a logarithm function or something, I go ahead and put a dot there to make it very clear that e to the t is a separate function that's being multiplied and not part of the argument of the logarithm. The other thing that you can do is put the e to the t in front, but I prefer not to do that because that obscures where the e to the t came from. And we get plus arctangent t e to the t. All make sense? Okay. Now, the last element of this that we haven't discussed as much, because I kind of been operating under the assumption that if I asked you to do this, you all would be in okay shape to do it. But that is how to handle things like initial values. Okay, so for instance, if we had this set of initial values that were being applied to the system, we need to make sure, of course, that we can figure out what C1 and C2 are based on this information. Okay. Now, for problems like this, where we have kind of a complicated expression for the particular solution, we just kind of have to plug it in and ride and see what happens, right? See where we go. So we're going to get C1 e to the 0 plus C2 0 e to the 0 minus 1/2 the natural log of 1 plus 0 squared e to the 0 plus the arctangent of 0 times 0 e to the 0. And this whole thing equals 1. And we're pretty happy about this because this is 0, this is 0, this is 0. Right? This one's 0 because the natural log of 1 is 0. Okay. So all of this together tells us that C1 has to be 1. And for this expression, we're going to have some more work to do. Okay, this one's not going to be so nice. We're going to start differentiating things. Okay. And so we look at our expression for y and start going from there. Let's go ahead and before we get into trying to plug things in, just do the differentiating part. C1 is 1, so I'm going to go ahead and plug that in. The derivative of e to the t is e to the t. The derivative of t e to the t is e to the t plus t e to the t by the product rule. By the product rule, the derivative of the natural log of 1 plus t squared times e to the t is going to be e to the t over 1 plus t squared plus e to the t times the natural log of 1 plus t squared. Right? And then the derivative of the arctangent times t to the t is going to be a triple product rule, except we already know what the derivative of this expression is, so we can just use that derivative in a single product rule, right? So I think about t to the t as just one function. So I take the derivative of arctangent, which is 1 plus t squared, and multiply that by t to the t. And then I add to that the derivative of t e to the t, which is e to the t plus t e to the t times arctangent. That's what I mean, right? Otherwise, you'd have to differentiate each thing separately and reorganize, and it'd be a little bit more of a mess. Okay. Now we got to start plugging in 0. If I plug in 0, it should be equal to -1. I get e to the 0 plus c2 times the quantity plus e to the 0 plus 0 times e to the 0 minus the negative 1/2 times the quantity e to the 0 over 1 plus 0 squared plus e to the 0 times the natural log of 1 plus 0 squared plus, there's a 0 in here, so it's 0, plus the quantity e to the 0 plus 0 e to the 0 arctangent of 0. Right? All kinds of stuff. Okay, so negative 1 is equal to 1 plus C2 times 1 minus negative 1/2. And what's the arctangent of 0? 0, right? So this is positive 1/2, right? Get subtracted. Do we agree? There's an awful lot of signs for us agreeing. Do we agree? Okay. All right. So that's basically the long and short of it, right? This is how we would go through, do a problem, put everything together, and go from here, okay? The differences between individual problems don't have anything to do with variations from the methods that we have discussed in today's class. It's just a matter of problems are different. You're going to have different types of functions that you have to integrate or differentiate and deal with the algebraic details for when it comes to putting in the values to determine C1 and C2 if you're solving an initial value problem, or being able to determine the functions U and V if we're talking about variation of parameters, or solving to find the coefficients for a method of undetermined coefficients type problem. Okay, so what I would like for everyone to do between now and Tuesday, which is going to be another review day for us, we'll work some more problems, and most of the time on Tuesday of next week, I'll earmark for a review of kind of the applications material so that you have more perspective on the things to expect to see on the exam on Thursday. Okay, because I know that that's mostly vocabulary based. I do want you to have the opportunity to go through and look at that and read through and take a peek. So brush up on that a bit between now and then, just so you're a little bit more familiar with it. I know that there are a lot of really technical calculations that appear in those things, okay? But I do, what I want you to focus on is making sure that you understand the meaning of natural frequency and how that relates to the other concepts that arise in sections 3.7 and 3.8. Because that's the main idea, is the damping and the forcing functions and all of that stuff. Their effects are pronounced by what happens with the relationship between the forcing functions and the effect of damping and the natural frequency of the system, the natural frequency of an undamped system. So the omega equals the square root of k over m. Sorry, make sure I had the coefficients right. Okay. Does that make sense? You will need to remember the natural frequency formula, yes, which is what you're thinking about. Omega naught equals the square root of k over m. I will be more specific about which formula I expect you to memorize on Tuesday. Have at your fingertips. It's not going to be a long list, but it's going to be the stuff that's theoretically the most important. Okay. And if there are special formulas that I want you to use on the exam or something, I will make sure that you know about those beforehand, or just put them on the exam and say, this is your starting point, work from this. Okay. But that stuff I'll be more specific about on Tuesday. What I want you to do now, between now and then, is the skill building work of practicing doing initial value problems for homogeneous equations, which were easy enough that we didn't take a close look at those today, but practice that. Method of undetermined coefficients and variation of parameters. Okay. Variation of parameters is the one that I want to make sure that you all definitely have a little bit of practice in, because it's the one that tests your integration skills, right? Okay. We didn't know going in how difficult this problem was going to be from a doing integrals perspective. Okay. Some of the exercises can get pretty tricky, and you have to remember things like how to do trig substitution or what have you, right? So do enough problems where you see one of those things or two of them and say, it's like, okay, I feel like I can do this if I absolutely have to. All right. I'm not going to give you killer integral problems on the exam, but I do reserve the right to give you ones that I would consider to be of moderate difficulty. Okay. Not super hard, but you have to think about it a little bit and remember how to do something like trig substitution, because that was an important skill from calculus 2 that opened up some doors for us in terms of integrals that we can deal with. Because I do know that in other classes you will see integrals where you have to compute things like arc length is a very common thing to be asked to do that has some important theoretical applications, and those trig substitution integrals arise very easily in arc length computations due to the way that the arc length formula works. Okay, so it's a crossover thing that I want to make sure that we're stay sharp with. Okay. And then also, thank you for those of you in the chat who sorted out the question. I was going to circle back to that, but someone answered it. It was about what happened to C1, and what I ended up doing was just plugging in C1 equals 1. All right, because we would have had to do that eventually in order to be able to figure out what C2 was. Okay, so that's where we'll call it for today. We'll come back on Tuesday, have another review day, and of course, as a reminder, we have our exam a week from today, and we'll work on that. Also, I sent out the Blackboard announcement about the stuff going on with the website that I put out in Blackboard. The old versions of the websites, I believe, were restored on a temporary basis. So you should have access to that material in the meantime. I am going to work behind the scenes to switch over to the new set of websites and the new web service. That won't be something that affects you. It'll just be the names of the URLs will change. Okay, so make sure that you access that material through Blackboard. If you happen to have favorited the URL or something for the table of contents, make sure that you're going through Blackboard. If something doesn't work, look at it in Blackboard, and the one in Blackboard will be hopefully the corrected version, at least through at least chapter 3, and then going forward as we move through the semester, I'll make sure that tries to stay updated. Okay. All right. Take care, everybody. Have a great one, and I will catch you next time.